Dear participants, dear friends, good evening everyone. It is my sincere pleasure to welcome all of you for this inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences to mitigate the negative impact of COVID-19 coronavirus infection on scientific thoughts and science-based actions. It is also my distinct pleasure to introduce you our tonight's speaker, Dr. Olexandr Isayev from Carnegie Mellon University in Petersburg, United States. He has kindly agreed to join us, and as part of our chemical science seminar series, he is going to give a talk on neutral networks learning quantum chemistry. Olexandr Isayev is an assistant professor at the Department of Chemistry, Carnegie Mellon University. He grew up in Ukraine, and here he obtained his Bachelor of Science and Master of Science degrees in chemistry from Dnipropetrovsk National University in 2012. Then he went to United States, where he obtained his PhD in theoretical chemistry from Jackson State University, and did postdoctoral work at Case Western Reserve University between 2009-2012. Following this, his scientific world line also passed through several universities and research centers, in particular through University of California, Los Angeles, University of North Carolina at Chapel Hill, and in 2012, he joined the Department of Chemistry, Carnegie Mellon University. Professor Olexandr Isayev's area of expertise include computational chemistry, quantum mechanics, and artificial intelligence. He is actively working towards the acceleration of molecular discovery by combination of artificial intelligence, informatics, and high-throughput quantum chemistry, as well as both generative and predictive machine learning models for chemical and biological data. Professor Olexandr Isayev is a recipient of 2017 Emerging Technology Award from the American Chemical Society and Graphic Processing Units GPU Computing Award from Invita Corporation. With this, I want to thank once again Professor Olexandr Isayev for joining us for this seminar and look forward to his talk. Olexandr?
Yeah. Thank you so much, Alikram. Thanks for the invitation, and it's my distinct pleasure. Hopefully you can see my slides. And okay, so thank you so much. Thanks for the opportunity. So what I'd like today to talk to you a little bit about our work, how we use machine learning to accelerate quantum mechanical calculations. And before I start and run out of time, I actually would like to acknowledge, people, students and postdoc in my lab who actually did the work. Funding sources from the National Science Foundation, Office of Naval Research, my collaborators in a group of Adrian Roberg, University of Florida, and ChemSpace, INAMIN, and various agencies that provide supercomputing resources for our work. Now, for me as computational chemist, one of my ultimate dream would be that all the computations, all the molecules we suggested, would work. So essentially, like angel would come and miraculously all your prediction are, have been correct and everything is working. And one of the idea and kind of the forward-looking direction of work in our lab or in many other labs is how artificial intelligence can accelerate molecular discovery. So you can imagine that the smart algorithms and machine would essentially be a hypothesis generation. They can come up with the structure of the molecule, maybe run hypothesis tests to verify this this idea. And then you can connect the small algorithms, for example, with a robotic platform to synthesize these molecules. This is one example of them. And also with high throughput biological or, can be analytical characterization of the properties of the molecule. And eventually you want to close this loop and therefore essentially have a, artificial chemist, an algorithm or a set of algorithms, a machine, can essentially do AI-driven automated molecular discovery. This is a big dream, but there are many academic labs and companies that work in these directions. So in my lab, again, we are a computational chemistry lab, so we work in this corner of developing algorithms. However, we do work with the experimental scientists who make a hardware part of this vision. And again, this vision is forward-looking and probably will not be easy to achieve. But you can think about it to making this AI platform as building a tower. So we, working on specific building blocks, and these bricks in these towers, and collectively, hopefully we can build a full tower and some kind of a foreseeable future. Now, one of the driving reasons why we use machine learning is this plot. So what I'm showing you here, for those computational chemists in the audience, you can characterize computational chemistry method in terms of their scaling, where n is the size of your of your system, number of atoms or number of electrons, and some kind of metric of accuracy, right? And therefore, if you look into do a simulation of realistic materials or proteins, and the system size is large, thousands and maybe millions of atoms, you typically have to rely on empirical force fields or methods that are linear or maybe quadratic in scaling, so you can afford the cost of these calculations. However, the problem is that uncertainty or errors can be very big, and therefore accuracy may be very low. However, if you want to reduce this uncertainty and properly describe molecules, you'll have to include all the fundamental description of quantum mechanics, and you have to climb this ladder and use more and more sophisticated method. For example, semi-empirical methods, density functional theory, things like Hartree-Fock, and finally post-Hartree-Fock, or so-called couple cluster theory. So for organic molecules, couple cluster theory is considered the gold standard and typically provides you what's called the chemical accuracy, 1 kcal per mole accuracy of calculation with respect to the high quality experiment. However, you pay extreme price of being, power of 7 of compute expense, and therefore this kind of simulation accessible only to small, small organic molecules, and therefore you cannot do simulation of realistic, proteins or materials, and therefore, and finally there is a, if you in principle want to do exact solution, so there's a full CI methods with the complete basis set extrapolation, and this is kind of a heaven, which is not practically achieved or anything pragmatic. However, the promise of AI and machine learning methods is to push our methods in this left corner, where we can take advantage of using our quantum mechanical data and approach to accuracy to these methods, but also maintain this high speed and linear scaling behavior because of the favorable scaling of the machine learning methods. And this is exactly what we do. And again, for kind of a general introduction, so this what a time-independent equation looks like. It's a partial differential equation, and you cannot solve it analytically for anything practical rather than hydrogen atom. However, if you look at this equation, and therefore we need the big machines to solve it. However, if you look for this equation from the point of view of machine learning, you can rearrange, and your ground state energy of your molecule would be the magic function f that depends on your input molecular coordinates. And from the point of view of machine learning, this is what's called the regression problem. And therefore, this is exactly what we do. You take a molecule, you pass it, in our case, we use neural network, and you predict energies. One of the advantages of neural networks, they're fully differentiable. Therefore, you can backpropagate and you can compute gradients and have forces and gradients on your atoms. And therefore, you can do various types of simulation. Things like geometry optimization, molecular dynamics, computing Hessians and things like that. And again, here I'd like to emphasize that, again, for decades, quantum mechanics perceived to be small, slow, sequential. You take a molecule, you use quantum mechanical methods to compute the properties. And this is slow and essentially one molecule at a time. However, as our computational resources grow, Adrian and I, we accumulate a big, unique database of molecules and structure of molecules and quantum mechanical energies and properties for many, many millions of molecules. And I think that the unique insight that we can now combine with proper molecular representation, we can use machine learning methods to predict properties, energies of for those molecules. And therefore, this historical accumulated data has a lot of value. So over the years, again, using this analogy with the Lego building blocks, we developed a number of different neural network architectures. And so there's a list of several of them. And again, starting from simple, simple architectures to very complicated, when neural network combined with the model Hamiltonian methods and so forth. So in this work, and in this talk, I explain a couple of of those architectures in more details. So in a sense, what we see is emergence of this what's called hybrid machine learned neural network force fields. So when we started our work in 2015 and published first paper 2016, so our method, what's called ANI1, so first generation of methods, represented total energy and approximate kind of medium to short range interaction with the neural network. And you can also use the empirical dispersion to describe van der Waals interactions. And here you can use empirical models like Green type dispersion, D2, D3 methods, so forth. In addition, just to energy, and I'll show you, we can predict, various per atom properties, things like partial atomic charges, atomic volumes, C6 coefficients. Therefore, in the next generation of ANI, we can also add long-range electrostatics and maybe high-order term as polarization if needed. We can also use more accurate description of the dispersion in what's called many-body dispersion methods and so forth. And also, alternatively, we have what's called AIMNet architecture, and I'll talk in details a few slides down the road, where this method is fully data-driven. We do not add any physical-based terms, and therefore all types of interaction implicitly are described by the neural network, and this is the fully data-driven methods. And these methods are more, machine learning plus physics-based terms for the long-range interactions. And the jury is still out, which of them is better, and we still work in both directions. So let me tell you, a little bit about how these things work. So ANI, it's a deep neural network. It's a software. It's a method, and so this is the chemical science paper which describe a lot more technical details if you're interested to learn. And to my knowledge, this is the first neural network-based potential, which is transferable for large classes of organic molecules. And for many, many cases of classes of organic molecules, it provides you an accuracy of the energies within 1 kcal per mole from our reference density functional theory. It also 5 to 6 order of magnitude faster than DFT calculation. And the way how it works, just to give you a kind of a flavor, to represent a molecule for the purpose of learning, you cannot just use Cartesian coordinates, because molecules come different sizes, different shapes, and this doesn't satisfy requirements to be a descriptor of the molecule. Therefore, we represent molecules which is called atomic centered environment. And you can think about it, it's a fingerprint vector that encodes for every atom. We have this environment that's centered on the central atom, and that span the radii, in this case, 5 angstroms. And within this cutoff radii, it's encode essentially radial and angular distribution functions of your neighbor's atom, and therefore give you a fingerprint, vector of numbers that encode this chemical environment. And essentially, you would see a neural network zoom in at one environment at a time, and the total energy of the molecule will be sum of all of these environments. Right. So this is the presentation. Then, to train how this will work, you collect a database of quantum mechanical energies and structures. So you take molecules. Again, each molecule, you featureize every atom, you compute this environment, you pass this environment for every atom through a neural network, and you have this essentially fictitious, local energy of this environment. You sum them up, and then you look for the error of this. Now this is the total energy of the full molecule, and now you compare with ground truth or from the quantum mechanical energy. You compute the error, compute the cost gradient, and update the weights of your neural network. So you do the standard, training of the neural network, and you iterate until your neural network been trained. So if you want to do the simulation, then this became this essentially pre-trained neural network. It's a Python function. You can plug it into your favorite simulation packages, for molecular dynamics or any kind of simulation, and then it serves you essentially a black box. Your feed molecular geometry, it gives you energy and forces, and you, as usually, do normal simulation as usual. So what we have currently available, we parameterize 7 elements. As you can see, those are most important biogenic elements: carbon, hydrogen, nitrogen, oxygen, sulfur, and a couple of halogens. So this is already published, publicly available. And if you draw me any organic molecule with these elements, will give you energy and forces. We have more elements in the progress. Again, we continue for more non-metals. We also exploring for also metals, salts, things like that. Again, for computational chemists in the audience, our choice was particular DFT functional called omega B97 XD. This is range separated hybrid functional from Martin Head Gordon group. And over the COVID period, we also switched a little bit modern. So this functional been developed probably 10 years ago. We switched for a little bit more modern flavor of these functionals. Also, switch from double zeta basis set to a triple zeta basis set. And also we have, again, a neural networks and parametrized on the couple clusters simulations as well. One thing, as I think is a very interesting feature of the machine learning methods, is that we can also have an idea of some uncertainty, how accurate or how confidently a model think it can predict energy and properties. And again, if you're interested for mathematical formulation, there is our journal Chemical Physics paper 2 years ago. But just to give you an idea, is what we use what's called the ensemble disagreement. So imagine we have a prescribed recipe how we can train several independent neural networks. And then you, in certain phase space, you made the prediction of energy and forces. And what you can observe is that there is this, as you can see, there is a certain region where this the predictions agree, and a certain region where predictions disagree. So you have a large deviation between these predictions. Since we use quantum mechanics as our ground truth, we can query it and essentially have exact oracle to tell us what is the exact energies. And what we show in this paper, and also many other scientists show in different domains, that when this disagreement is large, this is typically indications that we have either bad data coverage or a model overfit. But the good thing is that in principle, you don't need to do quantum mechanical calculation. You just need to compute this measure of disagreement to kind of give you an idea when you have this bad data coverage. And we use this ensemble disagreement essentially to indicate, how model is confident or not in the accuracy of prediction for energies. And just, quickly show you one quick example. So this is a simulation, again, with any neural network, one molecule in the droplet of water. And what here on the left I'm showing you, so it's a molecular dynamics snapshots, and this ensemble disagreement for every atom. And as you can see here, it starts, all values are small, but then this one pesky atom that's, essentially this ensemble disagreement is explored. It's very, very high, and you can easily see it here. And so this allows us to, find the problem. So we look for this atom. It actually was one of the oxygen of the water. And what essentially happens, since this is a model in development, at this point when this disagreement became very high, what I'm plotting you here is actually this HOH angle of the water molecule. So this is, this angle of water. And this particular water molecule started to behave weirdly. So this angle became very large and essentially started to approach it like a flat. And this is unphysical. And you see this, increasing of this angle. But essentially this metric allows us to find this artifact. And therefore, this is the way how to improve and monitor the accuracy of these simulations. And therefore, this is a very good feature to have in contrast to a classical standard force fields, when you cannot do these uncertainty quantifications. Now, just a little bit more in terms of the accuracy of the energy. So here on the left, what I'm showing you here, again, with respect to the quantum mechanical simulations, with the very wide window of energy, about 300 kcal per mole. Again, the potential systematically provides you an accuracy from 1 to 2 kcal per mole in terms of root mean square error. And here on the right, again, what I'm comparing here is the potential energy surface for the several of these molecules and how the potential energy surface was plotted. I'm picking a couple of these dihedral angles, and I start to rotate, and basically you can build, this 2D potential energy surface map. Here on the right is quantum mechanics. On the left, this is our potential. And as you can see, in many cases, you can hardly see the difference. So this is, again, summary statistic for the error for all the full potential energy surface. But what is also apparent that a neural network can reproduce even the smallest, you see these kinks in this potential energy surface, all these little feature structures. And again, this is very, very hard to do if you ever fitted standard classical force fields. Again, the same story with the accuracy of molecular dynamics and the forces. This is an example of ab-initio molecular dynamics versus molecular dynamics using the ANI potential. Again, energy, in terms of energy within 1 kcal per mole for this particular GSK, drug-like molecules, and the accuracy of forces. So this is the error of the force component, magnitude of the force components within 3 to 4 kcal per mole per angstrom, which is again very, very accurate. Now, let me show you a little bit more practical applications. What you can do with this now. You can generate, three-dimensional structure of the molecule. You can, help, pre-optimize molecular geometries for small organic molecules. I think the results in part might quite wider as well. So force fields are used to compute protein ligand binding free energy. And again, it's quite expensive simulation because you need to, do molecular dynamic simulation of protein ligand complex, typically box of water. Typical performance is for the well-behaved proteins or the accuracy of this free energy simulation within 1 to 2 kcal per mole. However, because classical standard force field parameters are very simple, form, in some cases that leads to unphysical torsions for small molecules and all kinds of error. And also standard force fields have very hard time to describe this coupling between these multiple torsions, thing I show you here. So this is an example. Again, we have this very recent preprint, and this work is collaboration with the lab of John Cadera, New York. And so what we did, we take this particular protein called TYK2. This is the kinase. This is a human kinase protein, which is important for, in cancer. But also, this particular protein has very high quality binding free energy, experimental binding free energy for the series of these compounds where R, you see this is a series of the congeneric compounds with this substituents, and this is the actual free energies. So here on the left, this is comparison of computed free energies versus experimental free energies. And so the shaded gray area, this is the region with acceptable errors. So if you look for the summary statistics, so root mean square error for the binding free energy, it's actually 1 kcal. It's not bad. However, if you look for R square, so the correlation, essentially the ranking of these molecules, it's 0.4. And this is because of these outliers where you have much larger error than some of the other molecules. And therefore, this accuracy is not good enough for the practical drug discovery. So what we did is essentially in the spirit of what is known QMMM calculations, you can also do hybrid ML-MM calculations, where at this point you can use a neural network to describe a behavior of our ligand in the system. However, the behavior of the protein and the water around it will still be described through standard force fields, because at this point we have parameters only for small molecules. We don't have protein neural network protein force field yet. So, and then you can essentially write appropriate thermodynamic cycle, how to compute these free energies, run the simulation, again the technical description in this preprint. And therefore, again, if you look for this absolute binding free energy calculations on the left, again using the force field, state-of-the-art methods, what we have. Right, again, if you use force field with ANI, this is what you get. Clearly see, right? We have substantial reduction of error. Our RMSC dropped twice, right? From 0.97, essentially from 1 kcal to half. But most importantly, R square correlation rose from 0.4 to 0.86, double. And again, this is now acceptable quality, high accuracy free energy simulation for protein ligands. And again, why it's happening is this is another application of our method for, interestingly enough, for a different kinase, but the story is the same, is that when you feed a potential, force field parameters for the ligand, this is the map of potential energy surface, what you get out of the force field. This is what quantum mechanics tells you, high accuracy quantum mechanical energy. And you can see that minima and maxima doesn't even close. So this is the quantum mechanical minima, which corresponds to actually to a maxima in the force field. This is what ANI will give you. And you can see very high accuracy. And because of that, you can describe, conformation of the ligand much more accuracy. This will give you this boost in the accuracy of free energy simulations. Again, the current feature of our software, again, as I told you, available elements. Code on GitHub, you can do geometry minimization, things like analytic hashing, molecular dynamics. We have implementation of periodic boundary conditions and things like that. In the last 15 minutes, let me show you a little bit more advanced that can we go beyond just fitting the models to an energy? Can we also add more physics to it, to our machine learning? And again, we can continue in this analogy of building this Lego building blocks, but now we can use this analogy for working with the neural networks. And now essentially playing with these Lego blocks to play with different architecture of neural networks. Again, this is again our ANI architecture, and this is very simple. So you take your molecular coordinates and essentially encode atomic environments through this particular angular and radial distribution functions and pass through a neural network. So this the shaded in blue, this is our mathematical transformation. The things in green, this is our neural network, and this in orange or yellow, this is our predictions. Now we try to again play and see if we can improve this architecture. And for example, this is what's called our AIMNet architecture, where we improve this with a couple of things. So first, we can also make our embeddings, our representation of atoms, to be learnable as well. So now we have an additional neural network building blocks. We can also improve for the long-range interactions, having these update blocks that would essentially pass messages from environment to environment and accounting for the missing long-range interactions. And thirdly, we can also, again, train to multiple different properties instead of just for energy. And hence, this is our what's called AIMNet architecture. And so AIM stands from atoms in molecules. So this is inspired by the Bader theory of atoms and molecules. So we have essentially analogies that these vectors, these embeddings that describe atoms inside our molecules, essentially consistent with our neighbors because of this messaging and updates. And this is much more, larger, more complex architecture, has 30 layers and 1 million parameters for that. I'll probably, in the interest of time, skip about the importance of these iterations. However, what I like to show you is actually, because now we have this learned representation of every atoms, we can actually build these maps. And for example, for our elements, each dot would represent a specific atom inside the molecules, and this is a few thousand of different molecules. And you can see each atoms are clustered, each atom types. They are actually a little bit resemble a periodic table itself. So you can see that hydrogen closer to halogens than to the carbon, kind of looks like this. And if you look inside the learned representation, for example, for carbons, you can see the small subclusters that a neural network learns about, the carbons in different types of environments. For example, with the, with electron donating or withdrawing, or kind of polar, non-polar environments. And also, what is interesting, that this kind of map differentiate carbons in this particular case with different partial atomic charges. So here you have very large positive charge, and this you have a negative charge on carbon. And again, it's all learned by neural network by itself. We didn't put it there by hand. Now, if you train to multiple different properties, so for example, in the original paper, we train to energy in the gas phase and also continuum salvation model. And therefore, now you can, for example, compare with real experimental observables, for example, free energies of salvation from the experiment. And this picture on the left gives you an idea about accuracy of the experimental free energies of salvation versus computed free energies. So the accuracy 1.8 kcal per mole, R square 0.8. And this accuracy is expected because, again, we are not taking the explicit solvent molecules. This is a continuum model of salvation. Therefore, this kind of accuracy is expected, and you cannot go much further, especially for very polar and charged molecules, because of the continuum model approximations. We can also explore a little bit and chemical reactivity. So, for example, what I showed you before was neural network been trained only to neutral organic molecules. However, we can also run a molecular dynamics for molecules in neutral, for example, +1 and -1 state, and we can compute the energy for these three states, but we can also compute the transformation from neutral to charged, +1 to -1, and so forth. Therefore, you can have the 7 options to compute this transformation. And then what you can do, again, you can train a neural network. You can train, for example, a neural network for each charged state separately. You can also kind of go to multitask and train one neural network and predict, energies of charged, neutral, +1, -1 states at the same time. But also, what's more interesting, we can also go one step further, and we can input our total molecular charge into the neural network, and let essentially a neural network deal how to distribute charges inside the molecule, and always predict the energy. So you're approaching more correct physical behavior when the discrete charge state would give you essentially the energies of this particular state. And just to show you again accuracy of the prediction for cations, neutral, anions, and therefore from these 3 states you can compute ionization potentials, electron affinity, and again the accuracy of this like 2 to 3 kcal per mole, very good correlation. And what is also interesting, since you condition your neural network on these total charges, what's happening in the neural network conceptually, we have this block, which we called neural spin equilibration. And essentially what it does, it's responsible for this long range non-local charge effects, where you can think about if you have this prototypical molecule, and again, you have 2 conjugated rings and electron donating, electron withdrawing group. So what happened if you attach or detach electron, so in the quantum mechanics, you can see the formation of the cation or anion, but also this non-local effects where you have this essentially like a spin wave, alternation of positive, negative charges, or rather spin charges in the QM. And the neural network essentially works in this way. It equilibrates through this message passing mechanism and re-equilibrate our charges and spin charges in the molecule. You can see as the number of these messages increase, you can see the correct behavior of alternative positive and negative charges as the neural network predicted. And therefore, again, this mechanism can be used in conjunction with the physics-based charge equilibration scheme like QEC as well. And the application of this is actually very interesting. That if you remember your quantum mechanical classes, there is a theory what's called conceptual DFT theory, or what's called the chemical reactivity theory. And in this theory, you can relate the derivative of the energy with respect to the total number of electrons in the system. and compute things like chemical potential, molecular hardness, electrophilicity indices, Fukui indices, again, global and local indices on the atom of the systems. Therefore, you can relate these quantities with the essential derivative by the number of electrons in the system. So what this architecture allows us to do, essentially compute all these indices, all these derivatives, by fully bypassing quantum mechanics, by modulating these incoming charges and computing these partial atomic charges and spins, and computing all these properties essentially fully data-driven inside the neural network. And basically, you don't need quantum mechanics and wave function analysis to compute conceptual DFT indexes anymore. Let me show you an practical example. So instead of showing the correlation, how good properties can be predicted. So again, in our paper, and so this is again the preprint link. We take an example of the electrophilic aromatic substitution reaction. So again, this is one of the classical, widely used reaction, and there is a in this reaction there is a problem of regioselectivity, depending on the stability of this sigma complex intermediate, depending on where this charge can be localized. Your reaction go in the particular ortho, meta, or para position. And to predict the regioselectivity of this reaction, the state-of-the-art methods are quantum mechanics. And in fact, there's a method called RegioSQM. Again, this is the link that use semi-empirical methods, again with the continuum approximation for the solvent, to essentially using semi-empirical calculation to enumerate all these complexes, and compare their energy, and therefore typically take 1 hour per molecule. It's fast, but it's not fast enough to do high throughput calculations and predict thousands and maybe millions of molecules for the need, for example, in drug discovery. So what we did, again, we took our model. We have not done any specific retraining for this regioselectivity prediction. And this is what we did. Again, we took all this data from paper. And this is, this validation accuracy, this is test accuracy on the data set from this paper. And as you can see here, if you just use quantum mechanics, compute this, conceptual DFT parameters, you get, 90% accuracy on the validation. If you combine quantum mechanical, this conceptual DFT indices with this RegioSQM, you go a little bit better. What we took, again, we take AIMNet, compute all these indices, but we also included this, learn atomic environment representation for every atom, and you can essentially match the accuracy of the quantum mechanics. However, in terms of relative time, we can do it 1,000,000 times faster. Therefore, you can essentially compute, very high throughput fashion very accurately. You can predict the outcomes for the chemical reactions. This is another example. Again, it's collaboration company Y. Unfortunately, I cannot disclose what reaction the company is, but the same story. Again, we can use AIMNet to predict the outcomes for this particular coupling reaction in this case. And again, this is the only way to approach the accuracy of QM calculation in the prediction of the yield, in this case, of the coupling reaction. So with that, let me finish with a couple of thoughts about, from my point of view, what is next. I think, this is really exciting times, and we see, maturing of this, field of machine learning. And I can think, just to wrap up with this movie. So what I'm showing you here, again, this is our the same ANI neural network. What we add a little bit of carbon-carbon bond breaking data. And what we run here, so this is a simulation of 4,000 atoms, 60 angstrom. This is a cubic box with the periodic boundary condition. So this 5 nanosecond molecular dynamics simulation with extreme temperature, so 2,500 degrees. very high temperature simulation. So when you run the simulation, you start from the essentially random hot carbon vapor. And what you can see is essentially formation of the graphene nanoflakes. You see formation of this fullerene, so this is a buckyball here, and the growth of the buckyball into the essentially larger nanotubes. And it's the same potential what we trained to a small organic molecules before, with addition a little bit of carbon-carbon breaking data. If you do quantitative analysis, probably the simulation is still wrong, and barriers, kinetic can be, very wrong. But conceptually, on the physics-based level, what I think it shows you that these machine learning models can learn physics. And despite the fact that we never show any nanotubes or nanomaterials, so the potential learn enough that carbon preferred to do conjugated 6-membered rings and stack them into the layers and the sheets. I think this gives us a promise that we can really push the boundaries of computational methods to allow realistic simulation of materials, reactions, and hopefully this will not take 50 more years. With that, let me advertise a shameless plug. I'm an editor of the journal. It's called Applied AI Letters. So if you do high quality, machine learning for the sciences and scientific application, please, submit a paper to our journal. It's an open access journal. And we're glad to see application of machine learning in chemistry, physics, and biology. And with that, let me finish and just leave you with the links. All our codes available on GitHub. Again, implementation of ANI, use of PyTorch as the framework in Python. We have ANI plugins for several packages, things like OpenMM, Amber, NumD, Tinker, LAMPS, AMNet, again, here in our GitHub. Most of our data is also available. So if you're interested in reference quantum mechanical data, DFT couple cluster, this is the link and publication. And again, since our methods are used globally, in Europe, US, Israel, a lot of companies and government entities in US and some of the companies in Europe, again, use this. With that, thank you very much. And I would be delighted to answer any questions.
Thank you so much for this very interesting and comprehensive talk. Please ask questions. You can ask questions using the chat button of the Zoom platform, writing a message, or you can also use microphone to ask questions. Please ask questions.
Don't be shy. Okay, let me read. I see there's a question. So the question is what the platform is you trained model deploy. So it's a pre-trained Python function. We tried mostly on Linux, but it should work Windows, macOS, doesn't matter. If you can run Python environment, PyTorch library, and have CUDA, NVIDIA GPUs, it should work. It might also work without GPUs, but with the GPUs, it's faster. So the question is, which features are more relevant for the estimation? Could you please elaborate for estimation of what? Energies or? The types of molecules. That's a good question. We didn't do analysis. So I cannot tell it what features are more relevant. But again, if you want to try, again, our code is open, and you can try and see how it works. So the ion channel. So the next question would be: is it possible to model ion channels by QM? It's a good question. Ion channels are challenging, and at this point, we do not have a good description of ions yet. Especially, you need sodium, maybe calcium, things like that. We're working. So internally, we do have a neural network parameter for water, liquid water. We started working with ions and into proteins, but no, we don't have a good model yet. In principle, that's what we want, but at this point, I don't think we can do any simulation of the ions. Have you used this neural network to 3D QSAR? We didn't, but please, it's a perfect example. You can use either new neural network or pre-trained and use it as soon as you have three-dimensional structure of the molecules. You can extract feature from it and use for QSAR application. No problem.
Dear Professor Alexander, I have a couple of questions.
Yes, please.
Can you hear me?
Yes, yes.
Thank you very much for this nice presentation. My first question is about a comparison of the tensor networks and neural networks. We can also represent the quantum states by using tensor networks. And I think tensor network simulations are also started to apply in biochemical molecules as well. Do you have any idea about this comparison? Is there an advantage of neural networks against tensor networks in the simulation of chemical molecules?
Okay, interesting question. I wish I have a good answer for you. I have not tried, so unfortunately I cannot tell you. But so far, what we see, there are many other types of machine learning methods. What we see, the neural network are indeed very flexible, works for many different types of applications. Not only to predict QM, but we also use it for screening, biological, drug discovery, other applications as well. But specifically, unfortunately, I don't know.
All questions, please.
So the question is, can we use quantum neural network for prediction? Yes, that's the whole point of our work. If you go, let me share my screen back, right? If you see, where is my pointer? So you see this GitHub links. So you go here, right? We have a package, the software in Python and pre-trained neural network. You go here, again, we have AIMNet pre-trained neural network, and you can use it in out of the box with a simulation. However, the caveat is that so far been what we parameterize a neutral organic molecules. So, so don't try to use for materials or liquids. It will give you an answer, but probably answer will be wrong. Again, we have also plugins for several simulation packages, like here. And if you use, for example, OpenMM, you can use any model inside OpenMM or soon Amber, NumD, and LUMS and do simulation. Okay, let me read. Okay, so the next question, is it possible to study with molecules having higher multiplicity radicals and biradicals? So what I showed you for the AIMNet NSE This is for anion cation radicals. We have not tried biradicals yet, but in principle, yes. If you want to train your own neural network to study biradicals, you can take our code and train for, your own specific problem. Or you can use this model for, for cation and anion radicals of organic molecules. It should work.
Dear Professor, I have a couple of more questions as well. And sorry for the background noise. I have a small kid.
Please, yeah, don't apologize. We all work from home these days. Yes, please.
Thank you very much. My next question is that this neural network representation, can this representation enable us to calculate the thermal state of a molecule instead of the ground state? Is it possible to obtain thermal state as well?
Yes.
To predict, yeah. And is there any computational cost when we compare it with the ground state simulation?
So again, what we've done so far, what I show you, we show ground state, we show cation radicals, anion radicals, things like that. So if you're interested, for example, like excited states or other thing, we do not have pre-trained model yet, but you can use our software, our models, to train neural network for your practical application. So if you're interested, for example, excitation and things like that. However, you will need your own training data, quantum mechanics, to train neural network for you.
Thanks. Then my
conceptually, yes, but if we have not done this particular application, somebody have to do it first to pre-train it.
I see. Then my next question is about this training. The accuracy of the reference method or the reference size of the reference molecules. Is there any restriction of this quantities in the applicability of the method? For example, yes. Yeah.
Absolutely. So if your QM method is wrong, neural net will give you a wrong answer, right? So you have to be careful what methods to use. Some methods may not be good, not applicable for the applications, and you probably know much better for what reference method to use.
Thank you very much.
Okay, so the question is, what is the quantum control on the effect of molecule structures to change their chemical properties? Could you please clarify what is specifically what do you mean by quantum control? I don't know if you can, Akar, if you can unmute or clarify. I'm not exactly sure what is quantum control.
Hello.
Yes.
I mean applying photons or electromagnetic field or electric field.
Okay.
As an open quantum system.
This is very advanced. We are not there yet. I think you can probably design a neural network that will describe it to you. But at this point, again, we just started. And to my knowledge, no one done this before. In principle, again, neural networks are very good and approximate a lot of different, phenomena and processes. But we have not done, and I don't know how to do it. So maybe you can do it.
I didn't mean to use the neural network for control purpose. I mean, without using neural network, by using photons or electric field to change the molecular structures, the angle of the binding of atom.
Ah, okay, I see. Yeah, so that certainly processes that can do it. But again, for kind of application, what we've done so far, there was no light involved. So there's no excitation, there's no absorption. So it's all ground state at this point.
Thank you. Thank you.
And again, if there are any follow-ups, so Alikram has my email. Please feel free.
Yeah, sure.
To follow up, and
So it seems that there is no more questions. There's one question from Professor Akol.
Yes. So, what is the limitation of our software? There are few, right? So, in principle, you can take the software, you can adapt to your own problems, but you will have to retrain neural network. The current limitation of applications is, if you read the paper, and happy to send you links, specifically to what we parameterize. So what we parameterize and what is publicly available, it's for isolated small organic molecules. You can do this hybrid MLMM simulation of proteins and ligands, but neural network, again, responsible only to a ligand part. Again, also the limitation would be, do not use it to do simulation of liquid water, surface. It is not trained yet. So it works at this point, what is publicly available, not in development, what we have so far. The publicly available work for, normal organic molecules.
Okay, more questions, please. So if no more questions, Alexander, perhaps we can stop here. What do you think?
Yes. Okay. Thank you so much. Thanks for inviting.
Thank you once again so much.
That's my pleasure. And, hopefully next time in person.
Yeah, next time I hope it will be in person.
Yes.
Face-to-face discussing all these exciting things.
Yes, thank you so much, and stay safe during these difficult times. And thank you so much, and have a nice
Okay, thank you.